Hi, this is Professor Dorr, and this is lecture number 3 of EE 310. In this lecture, we're going to discuss the source-free RLC circuit as it's presented in section 8.3 of Fundamentals of Electric Circuits by Alexander and Sadiku, which is an excellent textbook that we use in our course. Before we get started, I'd like to kind of show you a little graphic I made of what Chapter 8 is about. Or in other words, what are the problems that we're doing in Chapter 8? Because they're all very similar. And so I wanted to just make sure that before we jump into this lecture, you have kind of a bigger picture feel of what we're doing. So here's a little timeline. And time is, of course, starting over here, and it's going this way. And in the problems that we do, we're going to hear the system gets a long time to stabilize. Or in other words, the system was able to stabilize starting a long time ago, but the bottom line is it got to steady state by the time that you need to stop meowing. I'm giving a lecture. It gets to steady state by the time we get to t equals 0. And so at t equals 0, we look just slightly to the left and we see t equals 0 minus. That's right before the topology of the circuit changes. Because we remember the topology of the circuit changes at t equals 0 because we turn a source on or we turn a source off or we close a switch or something like that. But before t equals 0 and up and including t equals 0 minus, the system is in the steady state. So the next point that we're interested in is at what we call t equals 0 plus, or immediately after the switch changes. Come here, you rotten cat. Come here, you awful thing. Say good morning to everybody, Bella, and then disappear. Go somewhere else. You're interrupting me, and I don't appreciate that. Okay, don't claw me when you get down. Sorry, Bella's part feral, and she's not real used to being held, but she sure does like pestering me while I do these lectures, so I apologize for that. Okay, so at t equals 0, the topology of the circuit changes, and we have this epoch that we call t equals 0 plus. And we're going to solve for currents, voltages, and derivatives at t equals 0 plus. That's what we've done in the last couple of lectures. So the remainder of the chapter is going to focus on what happens in here and out past here. Or in other words, at t equals 0, we're going to get some kind of a big thud, or we're going to get a boing, or we're going to get some sort of transient behavior. And the next point in our timeline is a long time after t equals 0. And the system has now come into steady state again because whatever this transient was, it died out. So we call this t equals infinity. So reiterating, the system has a long time to stabilize and it ends up in a steady state at t equals 0 minus. Remember, steady state means that d anything dt is equal to 0, meaning that that none of the voltages, none of the currents are changing back here. And then at t equals 0, something happens and it initiates a transient behavior, and we get a thud, or we get a boing, or we get some kind of transient behavior, and then eventually that settles out and we get to time equals infinity, which is a steady state again. Okay, so this is kind of the roadmap of where we're going. So let's look at this circuit right here, and we can see that it's a series RLC circuit because the R, the L, and the C are all connected in series. And when I saw this in the book for the first time, I said, well, gee, wouldn't this circuit just do nothing? It's connected to ground down here, and there's no source of energy or anything like that. So why do I care about this? But here's the deal. This circuit will have initial conditions in it. There will be current in the inductor at t equals 0 minus, and there will be voltage across the capacitor. And of course, the current in the inductor is related to the energy in the inductor, because of course it is an energy storage element. And the voltage on the capacitor is going to make an electric field, which is going to store energy in the capacitor. So when you look at this, I want you to keep in mind that there may be some initial current in this inductor, and there may be some voltage in this capacitor, and we're going to start the whole thing off at t equals 0. And that's why we're going to get all that interesting behavior. So it's just a little detail, but it bugged me, so I thought it might bug you guys just getting started at this. So what I'm going to do is I'm going to do KVL. Let's see if we can make this smaller. Here we go. That's too small. Let's do KVL around this loop. So what I'm going to do is I want to add all these voltages up in this loop and sum them to 0. So let's see, for the capacitor, what's the voltage across the capacitor? Well, I know that the current through the capacitor is equal to C dV dt. So if I just divide both sides by C, I get IC over C is equal to dV dt. And if I integrate that, I'm going to get V. So here we go. Voltage across the capacitor is equal to 1 over C times this integral. And I'm not going to get too worried about these limits here because I'm going to take the derivative of it in a bit. So mathematically, I should be really concerned about these limits, but that's not what's going to get you through EE 310, and this isn't the math department. So our voltage across the capacitor is represented by this integral. So now let's write our KVL around here. We get the resistor voltage, the inductor voltage, and the capacitor voltage, and they're going to be 0. The resistor voltage is just R times I. The inductor voltage, we've got a nice expression for that. That's V equals L di dt. And we just came up with our capacitor voltage equation with this integral. So I've got kind of an ugly equation, and it's not the way you're used to seeing KVL, but it's KVL, and it's a good equation. So I'm going to eliminate the integral by taking the derivative of both sides of the equation. Of course, for the 0 here, that derivative is going to be 0. But for this term, I'm going to get R di dt. For this term, I take the derivative and I get L d squared I dt. And then for this term, I'm just going to take the derivative of the integral, and I end up basically where I started. So here is the resulting equation that came from my KVL. Now I'm going to divide this equation by L and rearrange things a little, and my second derivative is going to go over here, and of course it got divided by L, so the L goes away, plus R over L di dt plus I over LC is equal to 0. And this is a differential equation that we can solve. And what you might remember from your math courses is that some real smart people figured out how to solve this differential equation years ago. And the wonderful result that they left us with is that, first of all, this second-order linear differential equation has two solutions. And second of all, the solutions have the form I of t equals a times e to the st. So that's the beauty that we're left with by some real smart people. There are two equations, and the equations have this form. So what I can do is I can work backwards a little bit. And you may not be used to this because a lot of the problems that you've done in the past, the problems are kind of linear and you kind of go right from one place to another. But here, we're kind of using all the information we have to solve this thing. And the information we're going to work with is two solutions, and here's the form of the solutions. So what I see in the form here is I don't know what the constant a is, and I don't know what this constant s is. So I just got to figure those out. So what I'm going to do is, first of all, I'm going to note that I can take, if I know that this is the form of the solution, I can also write an expression for the derivative, for di dt, because the derivative of this expression with respect to time is going to just be as times e to the st. And the second derivative with respect to time is going to be as squared e to the st, because remember, we're taking the derivative with respect to time. That's a good place for you. You stay over there. Why don't you go to sleep? Bella always listens to these lectures, but she does terribly on my exams. So we know what these terms are going to look like because we know the form of the solution. And here's kind of the general expression saying the nth derivative of a e to the st is equal to a times s to the n times e to the st. But in the characteristic equation, what you'll see is all these i's are going to end up with an a in front of them. So for now, I'm going to toss that a. And I'm going to say that d squared I dt, that is s squared e to the st. di dt is s times e to the st. And of course, I is equal to e to the st. So this equation, our KVL differential equation, ends up looking like this. S squared e to the st plus r over L times s e to the st plus 1 over LC e to the st equals 0. Now what I'm going to do, I'm going to factor out e to the st. And the result I get is this equation here, s squared plus r over L times s plus 1 over LC equals 0. This equation is in the text, and it has this cool name. It's called the characteristic equation. And I want to describe a little bit about what the characteristic equation really is, because we started up here and we said, here's this circuit. And I said, hey, wouldn't it just do nothing? And then, oh no, well, it could have some initial conditions. It could have some current, it could have some voltage, blah, 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 blah. But now I'm saying, hey, here's a characteristic equation that describes that circuit somehow. Doesn't tell us what the voltages are, doesn't tell us what all the currents are, because we didn't know in the first place, right? But we say that it describes the circuit. And I want to give you some more insight into that. So what I do in my lectures, and I cannot wait to do that when everybody gets back in school, is I take a piece of copper pipe. It's kind of like the little piece of copper pipe that you'd see in wind chimes, but in reality, it's a piece that I have left from one of my plumbing projects out in my yard. And I take the copper pipe, and you got to work with me here, and we're going to drop it. So I drop the copper pipe, and it goes ding, 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 ding. And what I'm witnessing is, let's look at our picture. I'm going to start here with the copper pipe up in the air, and now I'm going to drop it, and that's my topology change, and it's going to go ding, right? Steady state. I held it up in the air. I dropped it and it hit the ground. That's the transient. Ding, or that's the topology change. Ding. And then my new steady state is the copper pipe is on the ground. Now, let's take the copper pipe or actually, before we do that, now let's take one of my juggling beanbags. And I'm going to start here with the beanbag up here, and I'm going to hold it so it's at steady state up here, and then I'm going to drop it. And it's going to go thump, and I'm going to get a thud. And the thud has some actual time associated with it because it doesn't go, it goes thud. See the time? Thud. And then it ends up at another steady state on the ground. So my copper pipe, when I dropped it, went boing, and my beanbag went thud. And if I take my beanbag and lift it to a higher level and drop it, it's still going to go thud, but it's a louder thud. And if I take my copper pipe and I hold it up higher and I drop it, instead of going boing, it's going to go boing, but the pitch was the same. The pitch was the same, regardless of whether I dropped it from 3 feet up or whether I dropped it from 10 feet up. And so the pitch, that ba, that is a characteristic of the copper pipe. It's not a characteristic of the initial conditions, which is how high I dropped it from. It's a characteristic just of that piece of pipe. So now let's come down here. This is the characteristic equation. It doesn't have anything to do with how much energy is in the circuit at time equals 0, or how high the copper pipe was when I dropped it. It just described the physical gizmo. Let's look at other things. I like old cars a lot, and sometimes when I get old cars, the suspension is pretty worn out, meaning the shock absorbers are often worn out, and I'll go down and I'll push down on the back of the car, and instead of coming up like this, like it would if it had good shock absorbers, the shock absorbers are all worn out. So it goes boing, and the back jumps up and down a couple of times. I push it down harder, and it still oscillates a couple of times. I push it down just a little bit, it oscillates just a couple of times with a different amplitude, because that system has a characteristic equation associated with it. So what we're going to find when we do these problems is that first we want to find the characteristics of the system, which are going to be whether it's going to give you a thud or whether it's going to give you a boing, and the characteristics of that thud and boing. Then we'll deal with the initial conditions to find out how loud that boing is or how big that boing is. So that's just a little significance into the characteristic equation. So what we're going, since we know that our solutions, because the smart people figured this out, our solutions are going to have the form I of t equals a times e to the st. And if it's a thud, then clearly s is going to be just some real number, right? Because a e to the minus 2t is going to be 0, or it's going to be 1 at 0, and then it's going to be a little exponential drop off. Thud. Hear the thud? Starts at 1, and then I've got this exponential drop off, Thud, and at t equals infinity, of course, it's actually going to be 0 because, sorry, s is going to be a negative number here. So I want to find s for a particular system. And I know that I'm going to get two values of s because we have two solutions. So two values of s looks like a quadratic equation to me. We can solve that. So I can get those values, those two values of s, without even caring about what the initial conditions are. So here we go. The value of the characteristic equation is that we can solve for S1 and S2 for our solution. And once we get that, the solution is going to be I of t equals some constant a1 times e to the s1t plus a constant a2 times e to the s2t. So let's solve the quadratic equation here, the characteristic equation with the quadratic formula. S1 and 2 are going to be minus r over 2l plus or minus square root r over 2l squared minus 1 over LC. And I'm going to say r over 2l, I'm going to call that alpha. And this business in here, well, we already know r over 2l is alpha, so it's alpha squared. I'm going to call this omega naught squared. And at this point, I'd like to introduce to you the idea and terminology that I use frequently of engineering toadstools. Because when I look at a pond and I see the critters in the pond, I suppose toads, but we don't have toads, too many toads in Southern California. But there are little toadstool kind of things on the pond. And the little critters will jump from toadstool to toadstool because they know that they're good places to land while they're going about whatever their critter business is. And in engineering, we take very complicated things and we make them simple. And the way we do that is by defining what I call the toadstools, or the little waypoints. And in this example here, this is kind of complicated. We have r over 2l and we have this big thing here. But what smart people have figured out after doing these problems for years and years and years and years is where are the little landing zones so that we can simplify the problem. And this is a perfect example of that. R over 2l, we're going to call that alpha. And we are going to call 1 over LC omega naught squared. And at this point where we are right now, we're saying, well, why do we need another term? But what you're going to find as the course unfolds is that alpha and that omega naught are going to be used for many different problems. And what they really allow us to do is quickly determine whether we have a Thud or a Boing. And so we've taken something complex and we've made it into something more simple. For example, a year after taking this class, you won't remember what R over 2L is. You'll have to go back to the book or my lectures to see that. But you'll know what alpha means, and you'll know that if alpha is greater than omega naught, you get a Thud, and if it's less than omega naught, you get a Boing, because those are your toadstools. And I've gone through my career trying to make sure I know what the toadstools are, because the way you do things that look complicated to other folks is we simplify them. That's what engineers do. And part of our skill is knowing where you can simplify and where you can't. Just a quick anecdote. I gave a lecture at an IEEE conference a few years ago, and it was at the Oceans Conference that they have in San Diego. And there were a bunch of scientists who came to my lecture. And it was actually funny because I kind of looked out over the audience and I was looking at all these people, and it looked like a Gary Larson cartoon. These people were totally scientists. And I gave them a lecture on control systems. And I went through and I did the Laplace transforms and I showed them the toadstools, and I used my silly little toadstool comment and showed them things like, in particular, damping ratio, and I showed them how to use the initial and final value theorems from Laplace transforms. And I really showed them how engineers have packaged control theory. We've packaged it so we can use it every day. And after the lecture, some of these guys came up to me, a couple of women too, and they said, gosh, we derived all this stuff with Laplace transforms, so our equations and our graphs all look like yours, but we never saw where the toadstools are. Your toadstools make so much sense. So anyway, you'll hear me say that a lot in this course and in EE 330, or when I'm talking about my guitar amplifiers. I'm going to talk about toadstools. And toadstools allow us to skip over lots of details and do big things, because big things are just combinations of a lot of little things. Okay, so I talked so long we probably forgot where we were. We are solving our characteristic equation. We're using the quadratic formula to get these two values of S, which are S1 and S2, that we will use in our final solution. And so we use the formula and we get something that looks like this, and our toadstools are alpha and omega naught. So let's look at this equation. We know that our solutions look like A1 e to the S1t, etc. And alpha is always going to be a real number. Okay, that's nice. Now, if alpha is greater than omega, then alpha squared will be greater than omega naught squared, and this will be a real number too. So if alpha squared is, or if alpha is greater than omega, then S1 and 2 will both be real numbers. And they will always be negative, but we'll go there later. So if S1 and S2 are real numbers, then let's look at I of t. Obviously, at t equals 0, this is just going to be A1 and this is A2, so the response will be A1 plus A2. And then as time goes on, we'll have a little exponential decay here, thud, and we'll have an exponential decay here, thud, and we're going to add our thuds up, and we're going to get a thud kind of response. And we're going to call that overdamped. That's the term that we use. That's another toadstool. Where will you see that toadstool again? You'll see it a lot in control theory in your control systems class. Now let's look at when alpha is equal to omega naught. That would be the condition where R over 2L happens to be equal to 1 over LC. And that's going to mean that S1 and 2 are going to be both going to be equal to minus R over 2L, because this factor, or this term, will be 0, because alpha is equal to omega naught, so this all becomes 0. And we call that critically damped. And for critically damped, I say, let's see, I used Thud and Boing, so I better call it a thump. But I don't get too excited about the critically damped case from a practical sense. In EE 310, boy, you got to know critical damp. But in reality, when I'm working with something in industry, R over 2L may be equal to 1 over LC, at a certain temperature or with certain components that I pull out of the bin because components have a statistical distribution on their values, and at a certain temperature. And in reality, what I'm saying is that critical damping is really a mathematical precipice. So I tend not to use it in my industrial work. Things are usually overdamped and underdamped, but this is EE310, so you want to make sure you know the math for critical damping. So now let's look at the next case. Alpha is less than omega naught. Well, now alpha is less, so that means that I'm going to have a negative in my square root. Well, that's going to make things interesting, because I no longer have a simple exponential in this equation here. I'm going to have a j term, and we're going to see that that's what's going to give rise to our Boings. Okay, so let's start off with the overdamped case. So we have all our circuit components, and the circuit components all have values. We get our alpha and our omega naught, and we find that alpha is greater than omega naught. Sometimes I'll say that our thuddiness measure is greater than our boinginess measure. Alpha being our thuddiness measure and omega naught being our boinginess measure. So this one is overdamped. We got a thud. And before I continue, I want to mention that I changed from I to R. We started here looking at a current, but what I want to do is I want to generalize a little bit, and instead of saying current or voltage, because it could be current and it could be voltage, it could also be sound pressure, it could also be position of that shock absorber on the back of the car, it could be all kinds of things. So what I use is I just call it R for response. Response of T is equal to A1 e to the S1t plus A2 e to the S2t. And so this is what my solution is going to look like. A couple of exponentials for overdamped. Now we're going to go to the critically damped case where alpha equals omega naught. And I'm going to just write the expression for the response of T. And here it is. You can see the equations in the text where they do a very nice derivation of it. Now let's go to the underdamped case. And this one's getting fun because it's got boings in it. And boings have pitch, and pitch is music, and I love music, and so I like the underdamped case. So in this case, we know that R of T is equal to A1 e to the S1t plus A2 e to the S2t, because that's what we started off with way up in a few pages above, where we said this is the form of our responses. But I can't plot this because S1 and S2 are complex. Why are they complex? Because alpha is less than omega naught, so I'm taking the square root of a negative number, so I get a j out here. So I can't plot this because these are complex. So what I'm going to do is I'm going to do what the seagull at Moonlight Beach does, and I haven't given you that analogy yet, but I will eventually. And I'm going to just start working with it and see what happens. So S1 and 2 are going to be minus alpha plus or minus alpha squared minus omega naught, but this rascal is negative. So what let's do is let's interchange the order of these, and now omega naught minus alpha squared is positive, but I'm stuck with a negative sign here. So what we'll do is we're going to change that negative sign into a j squared, because j squared is equal to -1. When you were taking math courses, you used I as your imaginary operator. But we use I for current in electrical engineering, so we call it J. MATLAB takes either because mathematicians use it and electrical engineers use it. Bottom line, we got a j squared here. We can take the square root of j squared and put it outside the square root. So we can do that. And we end up with minus alpha. Here's our minus alpha, plus or minus j, and here is another toadstool. Omega naught square root omega naught squared minus alpha squared is equal to omega d. So professor, why do we need another toadstool? Because smart people have already gone through this derivation and done it for hundreds of years, and they know that omega d is the frequency that it's going to boing at. So when I drop my copper pipe and it goes boing, is omega d. It's that frequency. So that's why we've got this toadstool here. All right, so let's put this back in our solution. We have S1 and S2, and they're complex, and we just shove them into our solution. And we can see that we had plus and minus, so that's why I have opposite signs going on here, because one of them is S1 and one of them is S2. Let's factor out e to the minus alpha t from both of these. That makes it look a little bit easier. And we're getting smaller, so we know we're probably doing something right, even though we don't always know we're doing something right. So now I'm going to remember Euler's identity, which is e to the j phi is equal to cosine phi plus j sine phi. And so I've got e to the j phi, and here's another e to the j different phi, or negative phi, I guess. Let's use it. So we'll substitute Euler's identity in, and our equation got longer again, but that's okay, we'll keep working with it. We're going to collect like terms, and from here, I convert this equation to this equation here. My e to the minus alpha t remains the same, but you can see I got sine omega d and cosine omega d's and j's and non-j's, and I put all that business together algebraically, and I get this. Now, I need you to take a leap of faith with me, because you're going to find later that A1 and A2 are complex conjugates. So what I'm telling you right now is just accept that, because we're going to use it. So since they're complex conjugates, let's look here. A1 plus A2, well, that's going to be 2 times the real part of A1, because since these are conjugates, the imaginary parts cancel. Now, don't take my word for that. Stop the lecture, get out your pencil, and make sure you're cool with that, because that's a really good little mathematical tool to have in your toolbox. And since it looks like a constant, I'm just going to call it this B1. So now things get a little more tricky here, where we have A1 minus A2. It's actually J A1 minus A2. So I'm going to split up A1 into its real part and its imaginary part. And I'm going to split up A2 into its imaginary and real parts. And I remember that A1 and A2 are complex conjugates. So that means they got the same real part. So these cancel out to 0. And when I subtract their imaginary parts, I get twice the imaginary part. So you see that right in this equation. So JA1 minus A2 is going to be J times 2J times imaginary A2. And I'm going to say, looks like a real constant to me, because I see J squared, that's going to be a -1. But by now, I'm not interested in signs anymore. I just know this is a constant. And I can now write my response using real numbers. response of t equals e to the minus alpha t times b1 cosine omega dt plus b2 sine omega dt. And we're going to see, you notice I was a little cavalier here. What I was really trying to do is just make things into constants, because we're going to do that same go backwards kind of thing that we did for the overdamped case and figure out what B1 and B2 are. But while we're here, let's just look at the form of this equation. I always like to plot everything because I like to see everything graphically, because that way I can rely on my intuition for certain things in derivations or proofs or inventions. I see an e to the minus alpha t. In electrical engineering, we typically call that the envelope of the signal. Why? Not because there's an e there. It's the envelope because it's multiplying a bunch of other stuff. So we have a cosine and a sine, so we know we're going to have some wigglies going on there. But I've got this envelope, and here's what that envelope does. See that? The envelope is scaling the magnitude of my sines and my cosines, and that's why we call it an envelope, because everything fits inside it. And my B1 cosine omega d, my B2 sine omega d, those are the wigglers in here. It's a sine or a sinusoid. And it is ringing, its frequency is omega d. Or in other words, remember I said the reason we're doing this whole omega d thing here, where's my omega d? Yeah, up here, the reason we did this toadstool is because we knew that that was going to be the frequency that the system would ring at. So here's our underdamped system. Here's our boing. So let's sing this. Boing, boing. Now let's take this little boing right here and let's put it in the broader perspective of our problems. Here we go. It sat there for a long time and then it went boing. And so that picture down below, it fits right here. Boing. See, I'm trying to sing the envelope, right? Boing. I don't know if you can hear the garbage truck outside there, but if for residential garbage, when the machine dumps the garbage into the garbage truck hold, residential garbage goes thump, right? But if it was a construction site and it was full of copper pipes and things like that, then you'd hear all these clangs when the garbage truck dumped the garbage can into the truck. Thuds and boings, and they're all around us in nature. So what let's do now is let's just summarize. We have an overdamped system, and it is characterized by alpha being greater than omega naught. And the form of the response can be voltage, current, sound pressure, whatever. The form of the response is A1 e to the S1t plus A2 e to the S2t. If the system is critically damped, or alpha equals omega naught, then our response is going to follow this equation, and we're going to get a thump that I say a little bit tongue-in-cheek, but thump it is. And if the system is underdamped, meaning that alpha is less than omega naught, now we get a boing, and we just went through the math to figure out what the omega d is. And omega d, let's give it a little more significance. It's the natural frequency of the system. It's a natural characteristic of that system. So when I drop my copper pipe and it goes boing, and then I drop it from a shorter distance and it goes boing, omega d stays the same. Okay, so what we need now to continue getting our solutions, because we want the whole solution, we want everything, we need to know A1, A2, B1, and B2. We need these for plotting to know our answer. And they are going to depend on initial conditions. And knowing those initial conditions are going to allow us to set up multiple equations in multiple unknowns, and we're going to end up with all the values in the real expressions that we can plot in Excel or see on an oscilloscope. Let's review just a little bit before we move on to solving for the constants in our equations. So for the source-free series RLC circuit, we have alpha is equal to R over 2L, and we have omega naught is equal to 1 over LC. And alpha and omega naught determine the type of response. They determine whether you're going to get a thud or a boing or a thump. And we have these generalized equations that give us the response under those conditions. And which of these equations you use depends on the relationship of alpha and omega naught. Now, you'll see that in my equation here for the underdamped case, or my Boing, I said that these constants, let's not call them B's anymore. Let's call them A's, because they're just constants. So now we're going to learn how to compute these constants, A1 and A2. So for the overdamped case, we have S1 and S2. The solution to our quadratic equation, characteristic equation, I mean, are going to be minus alpha plus what we have right here. And we have our response that's shown here. So what I'm going to do is I'm going to kind of work backwards a little bit. I know that this is what my response looks like, and I know that the response at time equals 0 plus is going to be A1 plus A2 because t is equal to 0. So if t is equal to 0, I have e to the 0 here, and we know that that's 1. So at time equals 0 plus, the response will just be A1 plus A2. Hey, that is the response at 0 plus. Isn't that what we did a bunch of problems that we solved for our 0 plus? Oh boy, did I say that funny. In our last lecture, we solved for the response at 0 plus. This is why, because we're going to use it to get A1 plus A2. Now let's take our general equation and just take the derivative of it with respect to time. It's an exponential, so it's easy. So it's just going to be A1s, because this s comes down here because we're taking the derivative with respect to time, A1s1 plus A2s2. Now let's substitute time equals 0 in there. So we're going to look for the derivative of our response with respect to time at 0 plus. So I'm going to just substitute 0 in here, and this exponential becomes a 1, and this exponential becomes a 1. And I can say that dr dt at 0 plus is A1s1 plus A2s2. And again, we say, hey, that's that dr 0 plus with respect to time that we calculated in that last lecture. And again, that's why we did it. So I have two equations in two unknowns. A1 plus A2 is equal to R of 0 plus, excuse me, and A1S1 plus A2S2, that's this one, is equal to dr 0 plus dt. And by inspection of the circuit, we know R0 plus and dr dt at 0 plus. And we know S1 and S2. So the only thing we don't know here is A1 and A2, but I've got two equations and two unknowns. The way I solve these is with matrices. I know you can solve for one in terms of the other and solve them that way, but that takes way too much time in an EE 310 exam. So your calculator handles matrices very nicely, and so for a problem like this, you want to be able to slap this in your calculator and get the answer in 20 or 30 seconds. Please don't make me look at your exam where you spent way too much time on one problem because you were eliminating a variable or something like that. Get good at using this feature on your calculator. In addition, in this class, you're going to have to solve complex matrices. And a TI to 84 won't do that unless you download some package that you can get over the internet. A TI 89 will, and your Inspire will. But I just want you to know that you will have to solve complex matrices in this class when we get into AC analysis. So, but the point here is you have a simple little 2x2 matrix, really good time to go become an expert at solving matrices on your calculator. Here's the equation you want to solve. You just get A1 and A2 by inverting this matrix and then multiplying it by these constants here. So the next one is the critically damped case. And I know that my response is equal to A2 plus A1t times e to the minus alpha t. And let's just look at the equation and kind of work backwards again. And at time equals 0 plus, let's see, this becomes 0, this becomes 1, and I know what A2 is because this just reduces to A2. So by knowing the response at 0 plus, I automatically know A2. Now I'm going to take the derivative of this equation. And that derivative is going to be equal, well, this term's easy. It's just going to be minus alpha A2 e to the minus alpha t. Here we have to use the chain rule. So we'll take the derivative of this and multiply this and the derivative of that and multiply it by that. You know how to use the chain rule, but we end up with two terms here. And now let's substitute 0 into our expression. Minus A2, with t equals 0, I just end up with minus alpha A2, and then plus A1, and this t is going to make this term equal to 0. So let's summarize for the critically damped case. A2, that's just equal to R0 plus. That's why I have a little arrow here. A1 is the formula we just came up with here, solved for A1, and we already know A2, so there's A1. I remember many years ago when I took this course. I took this course in probably 1981, and I remember seeing derivations like this, and they just seemed backwards to me. I was used to taking the math and turning the crank and getting from point A to point B. And I would look at something like this where we're saying, hey, we're taking the derivative of an equation and coming up with another equation, and that's giving us A1 and A2. And I thought, that is just evil mathematical trickery. And it actually bugged me at the time. Because what was so frustrating is it came so far out of left field, and I thought, this is not a tool in my toolbox. This is just some crazy, sneaky thing that, the professor is doing. And that was frustrating to me, because as a student, when I saw something, I wanted to be able to quickly compartmentalize it and put it in my toolbox. And I couldn't do it with stuff like what I just showed you. And then a zillion years went by, and I practiced and practiced and saw more and more of these kinds of things. And I got pretty good at doing it myself. And that's kind of the basis of the guitar amplifiers that we make. I just got good at using these mathematical tools. And where this one looked like it kind of just came out of left field, work with it, practice it, and it'll still look like it came out of left field, but keep doing it, and pretty soon you'll get pretty good. You'll be able to bring left field to you. So that's the critically damped case. Now let's look at the underdamped case. Here's our general expression. And it's cool because we've got our envelope, and then we've got our little sinusoid in here. And just as a quick aside, you might wonder, why do I need a cosine and a sine? It's because it allows you to start at any phase you want. I'm not going to go into that in more detail, but I encourage you, maybe stop the lecture, convince yourself that this little expression allows you to start your sine wave at any phase you want. And of course, there are different amplitudes here also. So let's substitute in time equals 0 in this expression. This becomes a 1. This becomes an A1 because the cosine of 0 is 1. This becomes 0. So I immediately know A1. It's just the response at 0 plus. Now let's take the derivative of the response. First, we'll take the derivative by itself, then we'll substitute in 0 plus. So again, I've got to use the chain rule. So I'll take the derivative of this and multiply it by that, and then I will leave this unscathed and take the derivative of that, and I get this big long thing. And now what I'm going to do is I'm going to substitute 0 in here, and my exponentials are all going to turn into 1s. My cosines are going to turn into 1s. My sines are going to turn into 0s, and here's what I end up with. Or if I take this equation and solve it for A2, I get this. And you can see that it is a function of my initial condition, my natural frequency, and A1. And I already got A1. So that is my underdamped case. So let's do an example. Now, here's a circuit, and we've been looking at circuits like this as we've been digging through the initial conditions. And now we're going to do the initial conditions, plus we're actually going to get this current I as a function of t. So let's triage things a little bit. First of all, the stuff on the left here, it just creates the initial conditions. Remember when we started this lecture, we said, hey, here's this little circuit with no sources in it or anything. How can it do anything? And I said, well, it's because it's got initial conditions. That's going to make it jump up and dance at time equals 0. And this stuff on the left is what creates the initial conditions. And after t equals 0, we're just left with that series RLC circuit. See that? So our strategy here is we'll first triage the problem and we'll say, what's going on with this thing? We'll kind of walk ourselves through it. Then we'll determine the topology. That's important because the series RLC is the first topology we're seeing, but we're going to look at the parallel RLC and then we're going to look at the general RLC later. So what you need to do is be able to look at the circuit after time equals 0, meaning this stuff isn't here, and say, what's the topology? And then we're going to get the initial conditions, I of 0 plus and di dt of 0 plus, because that's what we need to get our A1 and A2. And then we're going to get our S1 and S2, and they're going to tell us whether we're overdamped, critically damped, or underdamped. So we'll compute those, or if it's underdamped, we'll get omega D, which is the natural frequency. Boing. Sorry, no oing. That makes second order systems don't do that. Second order systems just go boing. We'll compute A1 and A2 and the time domain response. Then we're going to check everything. You're going to find in this class that I'm really big on checking your work. It's one reason I don't give you the solutions to the old exams, because I want you to be able to check your work both while you're doing homework or old exams or taking an exam. But it's my responsibility to show you a lot of different ways so you can check your work. So we're going to do that in this problem. All right, so here's our problem, and let's give it a quick triage. So let's see, the switch is closed at time equals 0 minus, it's in steady state. I got no current here. I got no voltage across the inductor. So really, I just have 4 ohms and 6 ohms in series. So I'm going to have a current of 10 divided by 4 plus 6, or 10 ohms. I'm going to have 1 amp going this way through that inductor. So that's going to give me, okay, my initial inductor current. Let's look at our capacitor. At t equals 0 minus, I'm going to have a voltage divider of 6 ohms and 4 ohms and 10 volts, and that's going to give me the voltage at this point. And I know there's no current in the capacitor, so that means there's no current in the resistor. So using KVL on the fly, I'm 0 volts plus 0 amps gives me 0 volts here. So I'm going to have my voltage divider voltage here, and I'm going to have 0 volts here, and that's going to give me my initial voltage across the capacitor. Okay, now let's open that switch. And what I know is that the capacitor voltage isn't going to change from t equals 0 minus to t equals 0 plus, and the inductor current won't change from t equals 0 minus to 0 plus. So that means, let's see, I'm going to have my 1 amp that I just computed going this way. So I got 1 amp going here. I got nothing here. That means I need 1 amp coming up this way. Really? Can I change the current in that capacitor instantly? Absolutely. Got a rule that even says I can. So at t equals 0 plus, this current will stay the same, but instead of getting it from this part of the circuit, that inductor is going to slurp it out of this side of the circuit. So that looks good. What's my topology? Well, at t equals 0 plus, the switch is open, so let's just ditch it for now. And let's look over here, and I see a series RLC circuit. And then I say, well, it's really, those two resistors can be combined. It's just a series RLC with 9 ohms, 6 plus 3 of resistance. All right. So now let's start moving. Let's see. Here was our triage, and this is all the stuff that we just did. And you can see I showed it at t equals 0 minus with the switch closed. And I got my inductor current of 1 amp. And my capacitor voltage is from that voltage divider. It's going to be 6 divided by 6 plus 4 times 10. And that's going to give me 6 volts. Of course, the capacitor current is 0 because t equals 0 minus is a steady state. Let's open that switch. When the switch opens, the inductor current doesn't change, but now it goes through the capacitor. And the capacitor voltage can't change quickly, so it's going to stay at 6 volts because that was its voltage before the change. So now let's get the inductor voltage. And KVL on the fly is lovely, but when things get too hard, I quickly just go back and do KVL the way we've all been taught to do it. So here's our circuit at t equals 0 plus. And I know this, I've got one mesh current going on. So here we go. Let's write our equation. 3 times I minus 6, because this looks like a voltage source because it's 6 volts, plus 6 times I plus whatever the inductor voltage is equals 0. Now this is different than what you've seen for KVL because, well, the first term was okay, 3 times I, but now I've got a capacitor and I called it a voltage source because at t equals 0 plus, that's what it is. And I went through and this was pretty straightforward, and the voltage across the inductor I just didn't know, so I called it V inductor. This is a perfectly valid KVL equation. So what I'm going to do is I'm going to say that my voltage at the current through the sorry, let me reset there. I know this current, it's 1 amp, because that is the initial condition of the current through the inductor, right? So I know this current is 1 amp. So that means I know this, I know this, I know this, I just don't know the inductor voltage. So again, normally when you do KVL, you're usually solving for the mesh current. Not in this case. Here you know the mesh current. So I want to know the inductor voltage, but I'm using KVL. So I solve that equation and I get my voltage across the inductor is going to be -3 volts. Now you might say, why am I doing this? And the reason is because I was asked for I of t, and I know that in order to get that A1 and A2, I need I of t, I of 0, 0 plus, and I need di dt. And to get di dt, I need the voltage across the inductor, because remember, di dt is going to be V divided by L, or V equals L di dt. That's why I'm getting this voltage. And now, just for fun, we know that at t equals infinity, all the voltages and currents in this circuit will be 0. And actually, I take that back. This isn't for fun because we're going to use this information that we're going to get here to check our work at the end. Now, I make the combination, the statement here that at t equals infinity, all the voltages and currents are 0. Really? Well, let's make sure. Let's formally do that. We could say, okay, this thing's dead, but let's formally define dead for this. At t equals 0, I know that I have no voltage across the inductor because it's steady state. I'm sorry, t equals infinity because it's steady state. So that means I have 0 volts here. And I know I have no voltage across, I'm sorry, no current through the capacitor. So that means I have no current anywhere in the circuit. So with no current, I have no voltage across here, no voltage across here. I'm steady state, so I got no voltage across here. So let's do KVL on the fly. No voltage drop, no voltage drop, no voltage drop, no voltage drop, in order for them all to add to 0. So I've shown that I have so with no voltage drop and no current, everything's dead. Now, that might seem like kind of a redundant exercise, but it really does hammer in the fundamentals. I remember when I started teaching this class many years ago, I told students, yeah, it's dead, there's nothing going on. And then I realized, hey, wait a minute, it's my responsibility to show that with the rules. And when I did that, it actually helped me too. So hopefully that helps you. So at t equals infinity, that current I sub t right here, it's going to go down to 0. We don't know what it's going to do in here, It's going to do something. It's going to go, but we know it's going to be 0 here, and that'll be a good way to check our equation. Okay, so let's get our initial conditions. I of 0 plus and di dt of 0 plus. And we've really done most of the work for that already. So I of 0 plus is equal to I of L of 0 minus, and we calculated that to be 1 amp. And of course, we used our rule right out of our rule book right here. Now, since V sub L equals L di dt, di dt is equal to V sub L divided by L. And we found V sub L during the triage, and it was minus 3 volts. So di dt is going to be minus 6 amps per second. So you can see that I have the two things that I need to get those initial conditions, or two of the things I need. I'm going to need S1 and S2 also. So let's determine the type of response. Now, here's what our circuit looked like, but we're going to combine those two resistances to give us 9 ohms. And now it's time to start using toadstools. So alpha is going to be equal to R over 2L is 9. Omega naught is going to be 1 over root LC, that's 10. Alpha is less than omega naught, or our thuddiness coefficient is less than our boinginess coefficient, so we are underdamped. So now let's figure out, so we know we're going to get a boing, right? So let's figure out the boingy frequency. It's going to be omega d, which is omega naught squared minus alpha squared. See how I'm using our toadstools here? So now let's get A1 and A2. And so I'm going to use the equations on page 10 of this lecture, because I'm not going to rederive this every time. I'm going to use those equations, and I'm going to write those equations down, and I'm going to use them when I'm taking these quizzes. So A1, we showed, was just equal to I at 0 plus, it's equal to 1. A2 is di is this expression here that we calculated, and we're going to put in the value that we got for A1, and we'll put alpha in there. We're going to put our initial conditions in there, and we're going to mix it all up, and we're going to get 0.6882. And we're going to put all that together, and here's our general equation for our underdamped case. Let's put our specifics in. Here's our answer. Now, what we don't do here is go to Chegg and see if we got it right. And what we don't do here is go to the back of the book and see if we got it right. And what we don't do here is write Professor Dorr an email and say, hey, you didn't give us the solution to your exams, and this is the answer I got. Is it right? Those are no, 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 no. We're going to check it, because you're going to know whether it's right. And then you're going to slam your fist down on my desk, and you're going to say, hey, Professor Dorr, this is the right answer, period. So let's learn how to do that. We triaged this thing out and said that I of 0 plus is equal to 1 amp. So let's see if our equation gives us that. Okay, here we go. 0 at t equals 0, my exponential turns into a 1. Cosine of 0 is a 1 plus this, the sine t is going to give us a 0, so we're going to put that there. And I got 1 amp. So our equation just told us something good. We triaged di dt at 0 plus was equal to minus 6 amps per second. So I'm not going to rederive that derivative. Let's just use the formula that we came up with for the derivative. And here it is. Let's put in our numbers at 0 plus. I substitute in my numbers, and I get minus 6 amps per second. I'm liking that. We triaged that the current at infinity would be equal to 0. And we note that in our solution, our first term is e to the minus 9t. So as t goes to infinity, this is, of course, going to go to 0. So I got 3 nice check marks here that are telling me that I got the right solution. All right, so a couple of more little things here. I have posted the LT-SPICE solution of this problem on Blackboard. LT-SPICE is a simulator from Analog Devices. Now it's Linear Technology Company. It's free. It's insanely useful. And we're not doing a project during the summer session, but normally we do a MATLAB and SPICE project. Learning how to use LT-SPICE is just totally worth your time. And I gave you this example on the website because it shows how to set up the switch for the initial conditions and everything like that. You can check any problem that you do for homework with LT-SPICE just by modeling or by changing my example. So take a look at that, dig into it. I promise LT-SPICE will be well worth your time. And once you get a little faster at it, you can put any homework problem in there, and you'll actually see those little derivatives at t equals 0. You'll see the exact time domain behavior that you calculate. Okay, so a lot of material in this lecture. I hope you'll go back, review it slowly, get a cup of coffee, get a glass of wine if it's late at night. Actually, no, don't do that. But take your time to go through it because this is a lot of material and it's not real easy to absorb. Hopefully I'll see you at office hours. Other than that, I'll see you in our next lecture.